Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, it's a real pleasure for me to be introducing Y.C. Tay here, professor from National University of Singapore. I've known Tay for almost 30 years. Back when he was a graduate student at Harvard is when we first met, and he ended up doing a PhD thesis in the database area on the performance of locking systems, which was really landmark work at the time and is still very relevant. He uncovered the abstraction of lock thrashing, which was behavior that had been observed, but nobody had really understood it from an analytic standpoint. And also, he did a good job in separating out the issue of resource contention for resources other than locks from the contention that arises from locks. People still read this work today. It's really as relevant now as it ever was. In general, his work is on analytic models for performance. It's most of his research. He recently came out with an introductory book on the topic, a monograph from the Morgan Claypool synthesis series entitled Analytic Performance Models of Computer Systems, that was just published last month. And you can see a pointer to that on his webpage online. As well, his webpage has a nice pointer to a lecture from a couple of years ago that he gave on universal cache miss equations for memory hierarchies. So he works on hard problems that are of pretty general interest to the issue of performance in computer systems. And today he's going to tell us on how to upsize a database so that you can use it for performance evaluation of database systems.
Yeah. So I'm from the other side of the ocean, and coming here, one thing I learned is always to have an advertisement. So, as you mentioned, this book just came out. It's less than 100 pages, and the idea is to introduce the elementary performance modeling tricks to people who have no interest in becoming performance analysts. They just need to have some rough model of how their system is behaving. The techniques are actually illustrated with discussion of 20 papers. Some work that was done here. So take a look. It's an easy read, I promise. So UpSizeR.
Stack of books, and are you going to autograph them later? Is that the idea?
That book should be read in soft copy because the 20 papers are hyperlinked. So I don't know how to autograph electronically.
I don't know. Do they publish hard copies?
They do. Yeah. But it's best read in soft copy. So this work done with students, Tai Ping Tian, Wang Tao, Ling Yuting, and Sun Yang. What I'm going to do is describe two problems. One I call the dataset scaling problem, and then the one the social networks attribute value problem, and of course introduce UpSizeR. UpSizeR is the first attempt at solving the dataset scaling problem, and it has within it what I call a strawman solution to the attribute value correlation problem, and you'll very soon see why I call it a strawman solution. So the motivation, we are in the era of big data, and big data means different things to different people. It could mean genome data or astronomy data, but in our context here, I'm talking about internet services. So some of these applications have insane growth rates, and I imagine if you are a developer of something that you aspire to be the next Twitter, you worry that your system is going to grow so large next month that your data set is going to grow so large next month that your system may not be able to cope with it. So if you are looking forward, you might want to test the scalability of your system with some by definition, synthetic data set, right? So how can you do that? One way to do so might be to use TPC benchmarks. TPC benchmarks allow you to specify the size of the data set. You want 1 gig, you want 100 gig, and it will generate it for you. And they have different flavors as well, and they are supposed to be domain specific. But they are not application specific. If you think about something like TPCW, which is supposed to be for e-commerce, and Amazon and eBay are both, roughly speaking, e-commerce, how relevant is this particular benchmark for Amazon or eBay is not clear. So the idea here is that we want something that's application specific. So rather than design one benchmark for this application and another benchmark for that, what we want is one single tool where you come with your data set and I'll scale it up for you. So the dataset scaling problem says that if you give me a set of relational tables and UpSizeR, the R is big, capitalized, because I want to emphasize that we're talking about relational tables so people don't misunderstand that I'm upsizing a graph or anything like that. So relational data table is D and a scale factor S, and I'll generate a data set that D prime that is similar. So here's where I use my probe. So you come to me, I'm UpSizeR, you come to me with a data set D, and I'm going to scale it up to D prime. And these two are going to be similar. The trick here, of course, is what does it mean to be similar, right? It could be statistical properties. The statistical properties in here must be similar to the statistical properties in here, or it could be graph theoretic. If this is generated by a user by a social network, then the social network here must be similar in some sense. So when defining the problem, I wanted since UpSizeR is supposed to work for different applications, I wanted a definition of similarity that is application that will work for any application. So our way around the problem is I'm going to imagine that when you come to me with the data set, you also have in mind a certain set of queries that you're going to run. And then the way you're going to judge whether D prime and D are similar is you're going to run the query on D prime and see whether it is what you expected. So that's how you're going to judge whether D prime is similar. So as suggested by this, when we conceived the problem, we were thinking about upsizing. That's why we call it upsizing, right? S bigger than 1, scaling it bigger than 1. But when I went around and talked to people, it seems that there's some interest in same sizing, making a copy that is the same size. Why would you want to make a copy that's the same size? Well, various scenarios. For example, I'm a vendor and you hire me, you have a data set and you hire me to do something with your data set, but you don't want to show me your real data set. So what you can do is you run UpSizeR to make a copy, a synthetic copy, and then you let me work with the synthetic data set. That's one possibility. Another possibility in the cloud setting is that people are, you may want to test a different layout for your data set in the cloud, or you might want to test a different index implementation or whatever. So you want to do all of this in the cloud, but you don't want to upload your data into the cloud. So what you might do is you generate a synthetic copy in the cloud. Or for people who already are working in the cloud and they want to do some experiments somewhere else in the cloud, you don't want to ship all the data there, right? So what you might want to do is you extract the statistics, you go there, and then you blow it up, and you get a synthetic copy. So various scenarios that you can think of. But actually, when I talk to a particular company, this is a big company, and they have no shortage of big data sets. What they're actually interested in is the downsizing. So why would you be interested in downsizing? For them, they see that their customers are struggling with trying to get a sample of their data set. So you have a data set that's year big, and then you have some prototype application that you want to debug. Now, heaven forbid that you run your prototype application on this big data set. So you want to take a small sample of the data set, and then you debug your application there. Sampling, what's so difficult about sampling? If this thing has 1 million users and you want to test your application on 1,000 users, you just randomly sample 1,000 users, right? What's so difficult? Well, it's not so simple because you might randomly sample 1,000 users, and these 1,000 users, somehow is connected to reference some object, and those objects somehow connected with some other users, and then you have to pull out those users, and it's like spaghetti, and in the end you get way more than 1,000 users. So for various reasons, you might also be interested in downsizing. Now, the UpSizeR algorithm will work for all these 3 instances. Okay, so I would like to say that there's no previous work, but I'll be lying. So I already mentioned TPC Benchmarks, and if you trace it backwards, you get the Wisconsin benchmarks that was done like 27 years ago. And in the Wisconsin benchmark, the relations are completely synthetic. And that particular approach, so meaning that they did not try to scale it up from some empirical data set. And that particular approach propagated down to the TPC benchmarks, and that's how they do it. So it's not that they did not consider the possibility of scaling out empirical data sets, but they have some they encountered some issues. When you try to scale up an empirical data set and you try to make the statistics the same, if your table has only 20 tuples, then you worry whether this 20 tuples is telling you anything about the underlying distribution, right? So for us, this is not a problem because the data sets we are dealing with nowadays are so huge that it's not a problem. Another problem that they encountered was why were they interested in these synthetic data sets? Well, they wanted to compare a particular vendor's offering against another vendor, right? Use these benchmarks to do this comparison. Now, when you want to do this comparison, you don't just have the data set, you actually run some queries. And you want to tune your data and your queries so that you can test the joint algorithms or the buffer management or whatever. So this tuning is much easier if everything is synthetic. If you use empirical data set, it's much harder to do the tuning. For me here, the way I formulated the problem.
Naive question. If I want to buy supplies for my company, why do I want to tune the queries? I want real queries, the ones that I'm going to run tomorrow morning to run my business. And the less they can be tuned, the more honest the benchmark will be. At least other benchmarking markets.
So you want to have a benchmark where you can test this vendor's offering against that vendor. So you want to tune the queries, etc., so that you can test what this system is actually doing versus what that system is actually doing.
Okay, if I want to do research on the database, yes. If I want to use it like a dumb user, no.
Mm-hmm. Okay, this was their particular argument. So for us, it's not an issue because UpSizeR doesn't worry about the queries. UpSizeR assumes that you have a set of queries in mind, but it doesn't make use of the set of queries, for example. Okay, so this is important to remember, right? In formulating the problem in formulating the solution, it's entirely possible to factor in the set of queries that you want to answer in doing the upsizing, but we don't do that. Okay. The third question, the third problem that they came up against was that scaling an empirical data set is hard. And that's saying that the data set scaling problem is hard. But it's been 27 years. It's a long time in this business, and it's about time we take another crack at the problem. Okay, so for you guys, I assume I don't have to go through this. I'm going to use the Flickr dataset. So in the Flickr dataset, users upload photographs and make comments and tag the photographs, etc. And my job is to upsize it, right? Okay, so in the Flickr dataset, you have a photo table with primary key and the foreign key values that indicate who uploaded the photograph. And then you have non-key attributes for the date, the size, etc. Right? So the user ID here is pointing to another table. So it's the primary key for another table with a username, user location, etc. And these are the non-key attributes. And then you have a comment table which says that this particular user commented on this particular photograph, and a tag table that says this particular user tagged this particular photograph. So what you get now is a schema graph. Okay. What assumptions do we use? So we start with the following. I'm going to assume that the primary key is just a singleton attribute. Sometimes it could be 2, but right now I assume there's just 1. I'm going to assume that a table has at most 2 foreign keys. So in the example that I'm using, the user table has no foreign key. The photo table has 1 foreign key. The tag table has 2 foreign keys. And the comment table has 2 foreign keys. So that's it. Okay? No 3 foreign keys. I'm going to assume that the schema graph is acyclic. I'm going to assume the degree distribution is static. Now, I haven't defined what degree distribution means. Let me give you the intuition first. So a user will post a number of comments. So if you take the histogram, you can change that into a distribution that says with probability so-and-so, you upload 1 photograph, 2 photographs, etc. I'm going to assume that this distribution is the same. So the degree distribution for this and the degree distribution for this is the same. That is not necessarily reasonable, right? Think about why we want to do this. We want to do this because you're afraid that when the data set gets to be this size, your system cannot cope. So there's a time element involved. So if you're thinking about loading photographs, by the time you get to here, everybody would have loaded more photographs, right? The tail of the distribution would have shifted. So it's maybe not reasonable to assume that the degree distribution is static. Okay? But for the time being, let's use that assumption. I'm going to assume the non-key attributes depend only on the key values. So the non-key attributes here only depend on the key values. That means, let's say in the case of the user table, these values here only depend on the key values, don't depend on the other tables, and don't depend on the other tuples. But this thing is completely synthetic. I mean, this thing has no meaning. What does it mean to depend on this? So what it means is that these values here can be independently generated. So when you give me the empirical data set, I'm going to mine it. I'm going to find out what's the distribution on the age, the sex, the names, etc. And I'm going to use those distributions to independently generate the values here. And later on, we'll worry about correlations. But at the moment, let's assume that's independent. Okay. So for the other for more sophisticated tables like this one, then this one in general is a function of this key values, right? See, so if I know that this user is a gardener, there could be a function that tells me what the key value should be, what the tag value, what the comments non-key attributes might be over here. So there is non-trivial. The correlation is non-trivial. Okay. And I'm going to assume that the data correlations are not induced by a social network, and that's not true for the Flickr network. But let's just use these simplifying assumptions for the time being. So UpSizeR uses 3 ideas. The first idea is a degree, and it's really simple. This user uploads 4 photographs, so the degree of Y to photo is 4. And user X made 2 comments, so the degree of X to comment is 2. The user Y made 1 comment, so the degree of Y to comment is 1. You look at it for a moment and you realize that what I'm talking about here is a bipartite graph. So every schema H induces a bipartite graph among the tuples here. And the degree is just talking about the degree of the bipartite graph. That's why we use that terminology. The next thing we worry about is the joint degree distribution. So I'm a user, I upload so many photographs, that's my degree, and I made so many comments, and that's my degree. And these two degrees are going to be correlated because the user likes to comment on his own photographs. Right? So we have to respect that correlation. In a table like comments, for something like a social network, you imagine that the users there might be a social network for gardeners, a social network for bird watchers, etc. And then the photographs might be clustered around flowers or kites or cars or whatever. And it's more likely that a gardener would comment on a flower. So there's some co-clustering distribution that we have to respect. So for a table with two foreign keys, the way UpSizeR deal with the correlation between the two foreign keys is to look at the co-clustering distribution. So these are the three ideas that we work with. The algorithm is quite simple. The first thing we do is we sort the four tables. So remember that there's a schema graph on the four tables. So when we sort it, the first one to come out, it would be the one with no foreign key. And then the one with foreign keys pointing to whatever has already come out, like this one, photo. And then the ones with foreign keys that point to whatever else has come out, like this two. And this will be the order in which we generate the tables. Okay, so how do we generate the user table? So your empirical data set has 1 million users. You want to upsize it to 2 million. Very simple. I just generate 2 million primary key IDs. And then for each one of them, I generate the rest of the non-key values. Okay, and that's done. Then the fourth. Sorry?
How do you generate the non-key values?
So remember the assumption that the non-key values only depend on the key values. And since in this case the key values have no meaning, that means that the non-key values is a function of this one in some trivial way. Right? So that means that I can independently generate the non-key values. So
do you satisfy any properties of the non-key values, like say there's a name column. The name column might have a certain length distribution or whatever.
Yeah, so I mine this guy for the name distribution, for the age distribution, sex, whatever. And then I use those to generate those values. Yeah. So at this moment I don't worry about correlations. So I just generate them independently. Yeah.
So for example, a name, it need not, in your model, it need not come from a dictionary. It could just be a string of characters of length 8.
Yeah.
Right?
So in this first cut version of UpSizeR, we are focused on the key values. So we don't do anything sophisticated with the non-key values. So the next thing to generate is the photo table. So how do we do the photo tables? Now remember that, so the first thing we do is we mine this for the degree distribution, degree from user to photo. Each user uploads how many photographs. So we know that distribution. I have 2 million users here. So what I do is for each one of them, I pick a degree value from the distribution. So user number 1 has degree 3, so he uploads 3 photographs. So user number 1, I generate 3 tuples, done. User number 2 has 5 photographs, I create 5 tuples, done. Okay. So that's easy enough. Now for the correlation, for the case where there are 2 foreign key values, right? What I'm going to do is I have to assign a degree from the user table to this column and a degree from the photo table to this column. Now, the degree from the user table to this column is correlated with user to photo, and that one has already been generated. So I have to take a conditional probability. Okay, no problem. Yeah, so as long as I respect that correlation. The other thing I have to worry about is the correlation in these 2 columns. So for the correlation in these 2 columns, what I do is first I generate a comment ID. I know the co-clustering distribution. So now I just assign the comment ID to a co-cluster. So let's say I assign it a co-cluster for gardener and flowers. Now, after I've assigned it to a co-cluster for gardener and flowers, I have to pick a particular gardener and I have to pick a particular flower. So if this gardener commented on 10 flowers and that gardener commented on 3 flowers, then with higher probability, I assign the comment to that particular gardener. So it's common sense. And this is what I do. I generate the ID, I assign it to a co-cluster, I pick a co-cluster, I pick a user in the co-cluster, in the user cluster according to the degree, pick a photograph according to the degree. When I'm done with that, I would have the 3 key values. Once I have the 3 key values, the non-key attributes only depend on the key values, so I can generate the rest of them. And that will be one tuple. And then I do this, so every time I assign a photograph or to assign a comment to him, I reduce its degree. I assign to a flower, I reduce its degree. And I do that until the degrees are 0. Yeah. And then I generate the tag table similarly. So it's very simple. The actual algorithm itself, the complete algorithm itself, has certain complications, but the basic ideas are already here. So relaxing the assumptions, suppose the primary key have 2 attributes. Then what we do is we create a synthetic attribute as a primary key. We work with the fake primary key. And then when we are done generating everything, we throw away the primary key, the synthetic primary key. Suppose it has more than 2 foreign keys. Now the co-clustering of the 2 foreign keys, we can use any algorithm. It's orthogonal to UpSizeR. If it has 3 foreign keys, well, just find me a 3-dimensional co-clustering algorithm and I'll work with that. Okay, it doesn't matter to us. Suppose the degree distribution, the schema graph is cyclic. And a good example of that might be the manager relation, right? A manager is also an employee, then you have a edge like this. I think we can deal with that. And if it's a cycle where one relation goes to another relation and it comes back, I think we can deal with that too. But if it's a arbitrary cycle, then I'm not sure how we should deal with it. Remember why we need to assume that it's acyclic? We need to assume it's acyclic because that gives us a way to sort the tables and we know who to generate first, right? But if it's arbitrary cycle, no, not just like this, but like this and like that or whatever, then where do you start? No, until somebody gives me a realistic scenario, I'm not going to worry about it. Right? Degree distribution is static. Well, so sometimes degree distributions are not static. For example, the number of countries in the world, you can't simply upsize that, right? So for us, what we do is we upsize it anyway, and then we hash it back. And that will change the degree distribution. A more interesting example is this case. Remember for the Flickr where I say the tail of the distribution has shifted. Okay, so suppose the degree distribution changes. There are various options we can use. One option is that when you come to me with the empirical data set, you also tell me how the degree distributions change. And then I will use that instead, right? If you cannot tell me how the degree distributions have changed, give me 2 snapshots, and I'll do an extrapolation from there. If you don't have 2 snapshots, I can go in here and I can mine the time column, for example, and deduce from the time you upload your photograph to extrapolate and say by next month how many photographs you would have uploaded. Many options for dealing with changing distribution. Yeah. Okay, so A tuple's non-key attributes may depend on its key attributes. So I'm assuming that non-key attributes only depend on the key attributes, don't depend on the other tables, and don't depend on the other tuples. So let's look at one example where it depends on the other tuples. How can we deal with that? So example from the tag, in the case of tag, for example, if you are a bird watcher, the tag values you use might be correlated somehow. For example, you're more likely to use bird and tree and sky, less likely to use car and bicycle or whatever. So in that case, there's some correlation in the tag values here. So how do we deal with that? So the way we deal with that is that, remember, the UpSizeR algorithm that I've described is based on the key values. So the tables have already been generated. Now you want to fill in the tag values to capture this correlation. So you know that, let's say this particular user used 13 tag values, and you're trying to find out, try to give him 13 tag values that are correlated. So what you need to do is generate a vector of 13 values for this particular user. Now what I do is I go into the empirical data set, and then I'll sample from it some tag vector. And this tag vector presumably will have some coherence. Now if I need 13 tag values, and this is too long, I just throw away some of them. If this is too short, I just add some more. And when I add some more, I have to respect the correlation among the tag values. Which means that when you give me the empirical data set, I have to mine the correlation in the tag values. It's very compute intensive. So if you try to capture all the correlation in the non-key attributes, this is going to be a major pain. But if that's what you need, then that's what you need. Okay. Up to this point, I think that we have the basic bag of tricks for dealing with classical data sets like banking data or retailer data, etc. But now comes the hard part. What if the data set were generated by social networks? The issue there is that if the data is generated, induced by social interactions, I have to understand what kind of correlations, what the correlations look like, so that when you give me the data set, I can extract from it the social interactions or the social network. Then I can scale up the social network and then induce the correlations, use that bigger social network and induce a correlation in the syntactic data set. So I need to know this mapping, right? I need to reverse engineer the social interactions. And I don't know how to do that. There's no literature on this. There's a lot of work on graph theoretic views of social interactions. There's a lot of work on algorithms for social networks. But as far as I can tell, there's no work on a database theoretic view of social interactions. If the relational database were induced by a social network, what kind of correlations would it have? And I've not seen papers of that kind. So since there's no literature on this, we just do some half-ass thing. So this is our hypothesis, that friends are similar, and because they are similar, their foreign key identities can be swapped. What does that mean? Okay, let me give you the example, right? So in the Flickr dataset, I'm going to define friends as two guys commenting on each other's photograph. Okay, we take that as the evidence that they are friends. And you can extend that to Facebook, writing on each other's walls, for example. Okay. Similar, how do I tell whether two users are similar? We can just look at the tag vectors. So if this guy uses this particular tag vector and that guy uses that particular tag vector, we take the cosine and we see, use that to judge how likely it is that they are going to be friends. Okay, so now how to replicate the social network. So this thing is generated by a social network, and I need to replicate that in this particular data set. So the first thing I do is I go in here and I extract all those guys who comment on their own photographs. This is a technicality. Almost everybody does that. And then because I define friends as commenting on each other's photograph, I can actually figure out who are the friends in this particular data set. I can reverse engineer it. Yeah. And then now I've generated the data set, the synthetic data set for that, right? I've already generated the tables. Now what I need to do is go and tweak the values in those tables so that I capture the social network, right? Up to this point, I have not yet done that, right? Okay, so first of all, I need to know how many pairs to tweak. So in the empirical data set, there are so many ages, so many pairs of friends. Now, for the synthetic one, I scale it up by S. Why S? Shouldn't it be S squared? So I checked the literature. This thing could be growing exponentially, but then the number of friends you have doesn't grow exponentially, except for some outliers. So my understanding of that is that in a social network, the way it grows is that you add more sub-social networks rather than one social network blowing up. So if it grows by adding sub-social networks, then yeah, it does scale linearly. So that's how we are going to do it. So I'm going to go in and tweak the values, the attribute values, so that I have this number of friends. So I'll pick m pairs, and I'll pick pairs from this set, and I will decide whether they are going to be friends or not by calculating the cosine. So if the cosine is 0.3, then with probability 0.3, I make them friends. Okay. So for each pair that I choose, so this guy commented on its own photograph, that guy commented on his own photograph. Now I swap these two, and when I swap these two, now they comment on each other's photograph. So that's how, and we do that for n pairs, so that's how we generate the social network for this one. Yeah. Okay. Enough of that. Now for some data. Yeah. So we've crawled Flickr to get a base set F1, and the data we store it in 4 tables. And so this is real values crawled, and then we take this base set and then we upsize it by 1, meaning we make a synthetic copy. Now these 2 values should actually be the same. It's just a floating point thing. So this is not a problem. So this is measuring the table sizes, number of tuples in these 4 tables. This table is generated by the degree distribution, and you see that the disagreement is already significant. Those 2 tables are generated by the co-clustering, and apparently it works decently. And then we crawl some more. So at this point, we have 1.5 million comments and 500,000 photographs. We crawl some more. So F2.81 is a data set where it has 2.81 times the number of users in F1. Okay. And we did a similar thing. And I'll let you judge how well this works. So this is the one with the most severe disagreement, and it's not clear why that is so. It could be that comments have some recursive property. When I comment on your stuff, you comment on my stuff, and it blows up, something like that. So this is comparing the table sizes. But I said that we should judge the quality of UpSizeR by looking at the queries, right? So we tested it on 4 queries, taking joins. Different number of joins, and here you see what we got. And I think it's pretty decent up to this point. And this is, you can look at it as, estimating join sizes. And one comment that I got from some people was that, this kind of estimate should be built into query optimizers. So anyway, so this is estimating, these are queries. Yeah.
Are these F9.1, for instance, is it a real database of Flickr or is it synthetic?
This is real, this
It's
is
real.
real.
So these are reals and these are your UpSizers.
Yeah, so this one is taking the original real data set, upsize it by 9.11. Yeah. So these are exercise. This is checking the whether we were able to capture the correlation among the key values. Now, what about the non-key values? So we tested retrieval on the non-key value like bird, the tag value. So the tag value, the bird here, for example. And the agreement is not so great now. It's okay here, but for the smaller size, it's not so great, and it's not clear to me why it's bigger for bigger. It's better for bigger sets and not so good on the smaller sets. We didn't try very hard. In the case of this particular query here, we are actually testing whether we captured the correlation among the key values, the non-key values, the tag values. And we didn't try very hard. As I mentioned, just capturing the correlation between, pairwise correlation between tag values is already very compute intensive. If you try to capture more than two, the correlation among more than two tag values is horrendous. So we didn't try so hard on that one. Yeah. I imagine that we can improve on these values. So up to this point, the social network is not in the queries. Now we want to test how this performs. What the query? If the queries refer to the social networks? What would the comparison? How would the comparisons look? So remember that UpSizeR deals with the query with the social network with the swap techniques. So now we have to compare the real query results against UpSizeR with and without swap. Right? We want to see how it goes. So the first query is retrieve pairs of friends. And you see that without the swap, you completely cannot capture. Right? You have millions of users and millions of photographs, millions of comments. The probability that you and I will comment on each other's photograph is basically zero. So you really have to go in and tweak the values if you want to capture the social network. Okay. Then the way we replicate the social network is to look at the similarity, look whether the two users are similar, and the way we check whether two users are similar is to look at their tag vectors. And so we want to see whether this is actually a good reflection on whether they comment on each other's photographs. So you retrieve X and Y who are friends and have at least 10 tags that they both use. And the agreement is still decent until like here. So maybe we can scale not by a factor of 10, but something less than that is okay.
What breaks at 9.11? It really looks like falling off a cliff.
We don't know yet. We should look at it. Yeah. It could just be that you have something with. So remember the way we build up these data sets is we crawled and crawled and crawled and crawled. It could be that there was something wrong with this particular data set. Maybe the way we did the crawling we might have messed up or whatever. It's not clear. So social interactions have structures, and this is the major issue. So one structure would be triangles. A friend of a friend is likely to be a friend. We didn't try. We were not so ambitious. We just wanted to see whether we can capture the V shapes. X and Y are friends, and Y and Z are friends. So can we capture that? And the answer is clearly no. Right. So what happened? It was doing well up to this point. So it turns out that yeah, we can scale up the number of friends accurately, but we cannot scale up the topology. It turns out that in Flickr, there are some hotshots with many friends like this in a star shape. And when we scale it up to F prime, we lost that star shape. The star shape just dissipated. So we have to figure out some way of doing it. Now, maybe it has to do with the way we use the tag. Remember, we replicate the friendship graph by looking at a similarity, and similarity is defined in terms of tag vectors. So currently, if this tag vector were bird, chicken, and this tag vector is birds, hen, then the cosine is 0. So, imagine you can actually do better than that, right? You put in an ontology or whatever. But my students tell me that you need a lot more than just that. You will fix some of the structural issues, but you can't fix all of it. So I described two problems. First is the dataset scaling problem, and as I say, UpSizeR has what I believe the basic set of techniques for scaling up anything that's a classical data set. But when it comes to the non-key attributes, there are all kinds of correlations in real data. And I imagine that the kind of correlations one application is interested in might be different from the kind of correlation another application is interested in. So if UpSizeR is to be a tool that will work for any application, we are going to need a lot of help. We can't do this ourselves. So we are releasing UpSizeR as open source, and I hope that if it is useful for people, then people will contribute by making the relevant changes, additions to them. The other problem that I introduced is the social networks attribute value correlation problem. Quite a mouthful. I can't figure out some shorter way of describing this problem. And we'll be the first to admit that the swap technique is ad hoc. It's not going to generalize. So what would be a general technique of replicating a social network in a relational data set? Here, we'll need some kind of theory to help us. Right now, because there's no database theoretic work on social networks, we don't know what to do. And if there was some theory built around the relationship between the social network and the relational data set, then it gives us something to work with. And I think it is a wide open problem. It's completely blank now. Anyone who gets there first will collect the citations, right? And this is what I encourage students to do in the universities. You guys are too old for that. Okay, I'll be happy to take more questions. Yeah.
If you run down UpSizeR at less than 1, how well do you predict the past? It's a lot easier to check than predicting the future.
Predict the past. We haven't tried that. We should do that. This is something that I intend to do in the next set of experiments. Yeah.
Give us a sense of performance, how long it takes.
I keep forgetting to get the numbers. So if you want to capture the non-key attribute correlation, it could take days. But this kind of numbers really depends on what hardware you're using and how many of them you throw at it. So I don't know how meaningful it is. If you don't care about the non-key attributes, you only are upsizing the key. You only worry about the correlation among the keys. I think for F1 it was some of the order of an hour to make a copy, to make a synthetic copy. Yeah. And
Okay.
F1 is 1.5 million comments and 500,000 photographs.
Is it naturally parallelized?
Some part of it can be parallelized, but I think there are some other parts that don't parallelize so well, I think. No, this sequence of generation cannot be parallelized so well. In general, here, these two guys both refer to these two guys. So these two tables have to be generated together. But I imagine that you can change the code so that you can generate these two in parallel. And furthermore, there could be some other, if you go deeper into hierarchy, there could be some other correlations that use a completely different set of keys. And then since those refer to a completely different set of keys, those can be generated independently of these two. So some part of it can be parallelized. But this particular sequence, it will have to be sequential, right? That one has to come first, then that one, then this two.
It seems like you could have a pre-processing phase that figures out what the parallelism opportunities are you're just analyzing foreign key relationships, really, to figure out where you can partition it.
Yeah. Certainly. You might not even need to do that. You just put them in the queue and then you just take them off the queue, whichever has been done.
Oh, I see.
Yeah.
Just generate the...
You just queue up these tables, right? Then if the processor is idle, you can just pull out the next one to generate.
You can also horizontally partition, can't you?
You mean each of these tables?
Yeah. I mean, you're following paths of foreign keys, but within a table, it seems like you could...
If you assume that these tuples don't have correlation, then you can generate these tuples in parallel, for example. This very fine-grained kind of parallelism. Yeah.
Anyone else?
Great, we are on time.
Great.